And this disk has radius r, and this inner disk, this inner little portion here, which we assume has no mass, has radius little r, and this one has mass m, and this one has also mass m. These two are identical. The yo-yo is released at 0 speed. It's going to rotate around this axis. Let's call this point C in the middle. Now the moment of inertia about this point C rotating about this axis is twice the moment of inertia of disks rotating about their axis of symmetry. Since I have two disks, I must multiply by 2 times 1/2 mr squared. So this is mr squared. So that's the moment of inertia about that axis. Now I'm looking at this situation from the side. This is this inner core, radius r, and the rope is wrapped around this inner core. And this is the outside radius, capital R. And so the forces, we have here 2 mg, remember, this was mass m and this was mass m, so we have to double that. And here we have the tension T in this rope. Clearly, we have again alpha equals A over R, because we have pure rho, so we can use that wherever we want to. We're going to apply Newton's law. The system is going to be accelerated downward. So 2 mg minus T must be 2 ma. That's equation number 1. And in the torque situation, I will take the torque relative to point C, which is the moment of inertia about point C times alpha. And that equals little r times t. If I take the moment of inertia relative to point C, it is this perpendicular distance little r times t. And that equals the moment of inertia about C, which was mr squared, times A divided by r. So I have already eliminated alpha. This is the second equation. So here we have two equations, and we have two unknowns, and you should be able to solve for both A, and you should be able to solve for T. It's completely identical of what we have done before. There really is no difference, except that the geometry is slightly more complicated. If now you're being asked what the angular velocity is, omega, when y equals h, so you also release this at 0 speed and you let it just unwind, and you want to know what the angular velocity is, or what the center of mass velocity is at y equals h. Now you have a choice out of two. You either use the value for A as I just used in the previous problem and you grind your way all the way through, or what I would advise you to do, which is just a little easier, you use the conservation of energy, and when you use the conservation of energy, you should get exactly the same answer. If I use the conservation of energy in my previous problem, the problem that I was so proud of, the object is going to move. So there's the previous problem where we had simply the object with mass m. The object is going to move over a distance h. So the energy released is mgh, Massachusetts General Hospital. That must go into the kinetic energy of the center of mass, which is 1/2 m center of mass plus 1/2 I of c times omega squared. So again, this is that previous problem whereby we had I of c equals km squared, mr squared. And this was that point C. Since V equals omega r, you can write down mgh equals 1/2 m Vc squared, omega squared r squared plus 1/2 km r squared omega squared. You have one equation with one unknown omega, and what do you find? You find omega is 1 over r times the square root of 2gh divided by 1 plus k. So not to confuse the issue, this is part of what I plan to do in my problem number 1. Notice that I find exactly the same value. There is no difference. This is precisely the value I found for omega. I think it dropped on the floor, but this is precisely the value we found for omega. We used it earlier by calculating A, massaging it all the way through. Here we use the conservation of energy. And I would advise you, in the case of this problem that we're dealing with now, which is this problem, what is it, 10 point something? I forget the number. It is 10 point, it's not my day, well, it's the day after, it's 10.10. So if you want to calculate now what omega is at y equals h or y v, center of mass at y equals h, I would recommend you use this technique. Of course, IC is now a little different from what we had here, but the concept is the same. So when you use the conservation of energy, it always goes faster than when you grind you all the way through and you use your A values. That's not so easy.